In this video, we'll go through the setup process to solve a problem using torque. This problem comes from OpenStax College Physics Chapter 9, number 17. In this problem, a person stands on a ladder which leans against a plastic rain gutter. There's no force of friction acting between the rain gutter and the ladder. We're asked to solve for the forces acting on the ladder. We'll start by drawing a picture to illustrate what's happening in the problem. Here is the ground. Here is the side of the house. And here is the ladder leaning against the gutter on the house. We'll give this a roof just because we can. Make it look a little more house-like. Alright, now we're given information about the mass of the ladder, the location of the center of mass of the ladder, the location of the person standing on the ladder, and the point at which the ladder contacts the gutter. Since this problem involves torque, we need to choose a pivot point for solving the problem. In this case, it makes the most sense to choose the bottom of the ladder as the pivot point. Therefore, we will make this position 0. We'll label it r equals 0 at that point. The center of mass is given as some distance above the base of the ladder. We'll label that r sub c for the position of the center of mass. The position of the person is also given as a measure above the bottom of the ladder, so we'll label that r sub p for the distance of the person from point r equals 0. We're also given the distance from the base of the ladder to the point where the ladder contacts the gutter. Since this is a corner of the house, we'll just call this r sub h for the position where it contacts the house. We're also given the distance from the base of the house to the bottom of the ladder. We'll call this r sub b. Next, let's try drawing a free body diagram for this ladder. Here is a point that represents the center of mass of the ladder. We know that there is a weight force, the force due to gravity, which always acts downward if we're on the surface of the Earth. We also have the normal force from the ground, which is acting upward, since this is a horizontal surface. This is the normal force from the ground. Then we have a normal force from the person standing on the ladder. That acts downward. This is a normal force from the person. We also have a normal force from the house that acts at an angle perpendicular to the ladder. So that goes in something like this direction. This is the normal force from the house. We also have a force of friction at the base of the ladder. This must counteract the horizontal component of the normal force from the house, so it must point in this direction. In this problem, most of our forces are vertical and horizontal, so it makes the most sense to base our coordinate system on vertical and horizontal directions. Let's take up to be the positive y direction, and to the right to be the positive x direction. We'll also want to know this angle between our x-axis and our normal force from the house. That angle corresponds to this angle geometrically. We'll name that angle theta. The free body diagram only tells part of the story in this case. We need to know about torque applied to the ladder, so we'll need to know the locations that those forces are applied to the ladder. So we'll draw those in our sketch as well. The force due to gravity acts downward at the center of mass. So this is the force due to gravity. The friction force acts at the base of the ladder. This is the friction force. The normal force from the ground also acts at the base of the ladder. Normal force of the ground. The normal force applied by the person standing on the ladder acts downward at the point where the person stands on the ladder. N sub P for normal force from person. The normal force from the house acts perpendicular to the ladder. N sub H. Now we'll list our knowns and unknowns for this problem. We're given the mass of the ladder and the mass of the person standing on the ladder. We're also given these distances, RC, RP, RH, and RB. RC, RP, RH, and RB. We can assume the value of g, the acceleration due to gravity, on the surface of the Earth. Now we'll list the unknowns. We're trying to find the forces acting at the base of the ladder and at the point where the ladder contacts the house. So we want to find N sub G, F, and N sub H. In order to calculate those values, we need to know theta, and we also need to know the force of gravity, F sub G, and we need to know the normal force from the person. Next, we'll list the equations we might need to solve this problem. We know the force of gravity is equal to the mass times g. We know the equation from Newton's second law, F net equals mass times acceleration, but we know that in this case the acceleration is 0 because the ladder is just resting there. So F net equals 0. We also know that since the ladder is not rotating, the net torque equals 0. And we'll need the trig identity. Sine of theta equals the opposite side over the hypotenuse. We also need an equation for torque. Torque is equal to a perpendicular force applied times the distance from the pivot to the point where that force is applied. So we've done the setup for this problem. We've drawn a sketch. We've drawn a free body diagram. And we've identified the locations that forces are applied to the object in our sketch. We've listed our knowns, our unknowns, and our equations. Next, we'll work through a symbolic solution for this problem. To start with, we know that we can calculate the force of gravity acting on the center of mass. That's just the mass of the ladder times the acceleration due to gravity, g. The normal force from the person on the ladder is equal to the magnitude of the weight of the person. So the normal force of the person equals the mass of the person times g. Next, we'll set up equations using F net equals 0. For the x component of forces, forces in the x direction include the friction force and the x component of the normal force from the house. So we have F for the friction force and N sub hx for the x component of the normal force from the house. The friction force is in the direction we define to be the positive x direction, so we'll put a plus sign before the F. And the normal force from the house has the x component in the direction we define to be negative x. And since there is no net force in the x direction, this sum of forces equals 0. Next, we'll look at forces in the y direction. We have the normal force from the ground, N sub g. We have the force due to gravity, F sub g. And we have the normal force from the person standing on the ladder, N sub p. We also have a y component for the normal force from the house, N sub h. And we'll make that N sub h y to show that's only the y component. The normal force from the ground and from the house both have positive y directions in our coordinate system. And the force due to gravity and the normal force from the person both are in the negative y direction in our coordinate system. And the sum of all these forces equals 0, since the net force equals 0. Next, we'll set up an equation for our torque. Since the net torque equals 0, we know that the torque acting in a clockwise direction must be equal to the torque acting in a counterclockwise direction. So torque counterclockwise equals torque clockwise. When you're constructing the torque equation, it's helpful to clearly define your pivot point before you get started. We've already decided that our pivot point will be here at the base of the ladder, where r equals 0. So I'll just write that explicitly here. Pivot is at r equals 0. This is the base of the ladder. In this problem, the only force applying a counterclockwise torque to the ladder is the normal force from the house. Forces applying a clockwise torque to the ladder include the normal force from the person and the force due to gravity. We know that torque is equal to the perpendicular force applied times its distance from the pivot point. In the case of the normal force from the house, that is applied perpendicular to the ladder, so the torque for the normal force from the house is equal to that normal force, N sub h, times its distance from the pivot point, R sub h. And again, the counterclockwise torque is equal to the clockwise torque. We determined that the forces applying clockwise torque include the normal force from the person and the force due to gravity. So then we have the normal force from the person times r sub p times the sine of theta. And we also have F sub g times r sub c times sine of theta. Now you should have all of the pieces that you need to solve the rest of this problem. Go ahead and give it a try. In case you don't know where to go from here, I'll go ahead and work through the rest of the symbolic solution. Now we know that sine of theta is equal to the opposite side over the hypotenuse, so that will be RB divided by RH. So let's write that up here. Sine of theta equals r sub b divided by r sub h. Now we can rewrite this expression in terms of quantities that we know. We still don't know n sub h. We'll leave that as that. We do know r sub h, and this equals n sub p, which is up here, m sub p times g, times r sub p times sine of theta, which again is up here, r sub b over r sub h, plus fg, which is also up here, and is m sub l times g times r sub c, again times sine of theta, which is r sub b divided by r sub h. Now we can simplify this expression by factoring out quantities that appear in both terms on this side of the equation, such as g, r sub b, and r sub h. So we can rewrite this as m sub p times r sub p in parentheses plus m sub l times r sub c, close parentheses, times g times r sub b divided by r sub h equals n sub h times r sub h. Now we can solve for n sub h by dividing both sides of the equation by r sub h. So n sub h equals m sub p, r sub p, plus m sub l, r sub c, times g, r sub b, divided by r sub h squared. We know m sub p and r sub p and m sub l, r sub c, g, r sub b, and r sub h. So we've now solved for n sub h in terms of only quantities that we know. Now that we've solved for n sub h, we can find the x component of n sub h and the y component of n sub h. The x component, looking at our free body diagram, must be n sub h times cosine of theta. And the y component is therefore n sub h times sine of theta. Next we can solve this expression for the friction force. Friction equals n sub hx, which we know is n sub h cosine of theta. N sub h cosine of theta. Since we now need the cosine of theta, we'll need to solve for theta. We can solve this expression for theta by taking the arc sine of both sides. So theta equals sine -1, which is also known as the arc sine, of the opposite side over the hypotenuse, so r sub b over r sub h. That will give us the theta to plug in there. I'll separate those with a semicolon. Alright, and then we can solve our last expression up here for n sub g. That's the last quantity we're missing from our unknown list. N sub g equals f sub g plus n sub p plus n sub h y. Oops, that should be minus. Since we had to subtract to get it to the other side of the equal sign. Now we'll substitute our other expressions for these values. N sub g equals m sub lg from this expression plus m sub p g from this expression minus n sub h times sine of theta, which is r sub b divided by r sub h. And now we've completed the symbolic solution for this problem. All that remains is to plug in the numbers.